Chapter 17, Lecture 3. In this lecture, we will begin talking about titrations. Now, titrations are a set of experimental techniques that are extremely important in chemistry, and they are usually applied to acids and bases, but they can also be applied to many other reactions. Essentially, it's a way of using a known concentration, say in this case of a base, to find out an unknown concentration. So a very important experimental technique in determining unknowns. With acids and bases, a pH meter is oftentimes used. Indicators can be used to show you where you should stop the titration. A pH meter can be used and give you even more information about the unknown. So what you're doing is you're trying to reach something called the equivalence point, and that's the point at which all of your base has reacted with all of your acid. Technically, that's the point at which you need to stop the titration, and then from there determine your unknown. So in this case, we show a beaker containing HCl. This is your unknown, and then here we have the burette, the device that's used for titrations, containing your known. And so by measuring how much known you add, you can find out how much unknown you have, because you know the relationship between the known and the unknown. In this case, the stoichiometric relationship is 1:1, as you'll see. So here, the acid plus the base, this is the famous acid-base neutralization reaction, which forms salt and water. Our salt is sodium chloride and water. So you know that you have 1 H for every 1 OH, so the relationship is 1:1, and knowing this relationship, you can then calculate the unknown. So what we're going to do here is actually we're going to keep track of the pH during the entire titration. We're going to take a much closer look at the whole titration as it proceeds, and especially we're going to keep track of the pH. So we're going to create a graph in which we graph the milliliters of sodium hydroxide added. This is from the burette, as we're adding to our beaker. And on the y-axis, we will measure pH throughout the titration. So at the beginning, from the start of the titration, because we have HCl in our beaker, we begin at a low pH. Notice we begin at 1, which corresponds to roughly probably a 0.1 concentration of HCl, and notice the pH slowly goes up as we're adding base, which makes sense. We're adding base, we're neutralizing the acid is disappearing, therefore the pH is slowly climbing. Now, just before we get to the equivalence point, remember this is the point at which the acid and the base react, and the equivalence point is right in the middle of this titration curve. Incidentally, the titration curve has an S shape. This is an acid-base titration curve. So right in the middle here, this is also called inflection point in mathematics. But the pH rises very rapidly. So we began rising at this portion, it's pretty slowly, and then we really shoot up in pH. And this is due to the fact that your acid is almost completely neutralized, and you are about to get into the base region, so you shoot through the equivalence point very, very quickly. So here we are at our equivalence point, and by definition that's where the moles of acid equals the moles of base, and the solution has water and salt. And so here is where technically the titration has ended. Now what you see here, these two bands are called indicators. This top indicator is called phenolphthalein. The bottom indicator is called methyl red. Now both of these indicators can be used to catch the equivalence point because they are spanning this vertical range. As long as you've got the indicator covering this vertical range, you can catch your equivalence point, and that's what you want the indicator to do. And then as you keep adding the base, notice the pH then goes above into the basic, so into the 11, 12 and then just keeps rising slowly, because now all the acid is gone. All you have is yourself OH in the solution, as is seen down here. So we can ask a question like this: how many milliliters of a 0.080 molar sodium hydroxide are required to titrate 40 milliliters of 0.05 molar nitric acid? Now, let's go ahead and write the reaction. It's important to be able to write the equation. That way we can see the relationship. In most of these cases, the relationship will be a 1-to-1. So we have ourselves nitric acid plus sodium hydroxide. Now, for most of these titrations, you'll see me use a single arrow, because most of these reactions lie to the right. They almost all go toward the product, so really there is no sense in talking about equilibrium. But you'll gain, you'll have, technically this is a double replacement reaction, if you recall, and we'll end up with sodium nitrate, which is our salt, and obviously water. Balancing the equation, we see that we need 1 for 1. So this is an important step, because if you have something, say, like calcium hydroxide, then you will require twice as much acid, and your relationship will not be 1-to-1, and that will change the math. So let's go ahead and solve this. Essentially, what we're trying to do is equal the moles of acid to the moles of base. Remember, at the equivalence point, moles of acid equals moles of base. So we're given our two solutions. We're given 0.080 molar base, and we're given 0.050 molar acid. Now we're given essentially how much of the acid we have. We have 40 milliliters of the acid, and we're asked how many milliliters of the base we're supposed to come up with. So the plan here will be quite simple. Let's find out how many moles of acid we have, and from there we will find out how many moles of base we have. Then, using the molarity of the base, we'll find how many milliliters of the base we have. So let's first solve for how many moles of acid. Remember, we are using molarity, defined as moles over liters. So in order to find moles, rearrange the equation, and moles is molarity times liters. So take these two numbers, take molarity, 0.050, multiply it by liters, so divide this by 1,000, and you get yourself 0.0400. Again, this is divided by 1,000, because we're going from milliliters to liters. So we get ourselves, go ahead and calculate this. This is going to be roughly 0.002, two significant figures, moles of acid. So we've added this many moles of acid at the titration, which means we have the exact same amount of base. This means we have 0.0020 moles of base. And knowing that we have this much base, we want the liters or milliliters of base. So back to our molarity equation, let's solve for liters now. Liters will equal moles over molarity, which means we plug in our moles, 0.0020, over our molarity, which is 0.080, and we get ourselves the liters. Go ahead and do this in calculator. And you get yourself 0.025 liters, multiply it by 1,000, and this gives us 25 milliliters of base. So in order to completely neutralize 40 milliliters of 0.050 molar acid, we need this much base. And we are here, remember, we are solving this problem at the equivalence point. We're going to now take a look at some problems that are not at the equivalence point, but sometime before the equivalence point. in the course of this titration. So we'll finish up this lesson with another titration calculation. And here is the general map for calculating titrations. So at any point before the equivalence point, we want to remember the titration curve looks like this. So we've just calculated at the equivalence point, but we can be asked about any point throughout the titration on this titration curve. And here is what we're going to do first. We're going to calculate how many moles of acid and base we have. Then we'll take the difference between the moles of acid to find how many moles are left over. Because you're adding acid versus base, and technically whichever one wins is going to be the one that's left over. They will neutralize each other, and one of them is going to be left over. And then you'll determine the molarity of the leftover moles by dividing by total liters. And if we have molarity of the moles of the acid or the base, because these are strong, these titration calculations are for strong acids and bases. What we'll be able to do is simply negative log to find the pH. And we'll actually practice this in the next problem. So here we go. Calculate the pH when 45 milliliters of a 0.100 molar sodium hydroxide has been added to 50 mils of a 0.100 molar HCl solution. So remember, we're putting acid versus base. And one of them is going to be left over. They will neutralize one another, and one will be left over. We want to find out which one and how much of that one will be left over. And then the pH will be based on him. So let's go ahead and begin here. Let's find out how many moles of each we have. So why don't we do what we can do here to help ease our calculations is we can set up the equation. Actually, for this one we won't set up the equation because we have strong acids and bases. Let's go ahead and directly find out how many moles of each we have. NaOH and HCl will react in a 1-to-1 molar ratio to produce, again, sodium chloride and water. So there's no need to, it's going to be 1 for 1. We don't need to double anything. Let's find out how many moles of acid we have, how many moles of base we have, and then we'll go from there. So we have 45 mils of a 0.100 molar sodium hydroxide solution. So let's find out how many moles of base we have. Let's multiply these two. Moles will be liters times molarity. So again, 0.045 times 0.100. And this is essentially like dividing by 10. So we get ourselves 0.0045 moles of base. In this case, OH minus from sodium hydroxide. Let's do the same thing to our acid. And we have 50 milliliters of 0.100 molar HCl solution. Let's go ahead and multiply these two together. Our moles will be 0.050 liters times our molarity. And in this case we get 0050 moles of H+. So here's the picture. We're putting these against one another. Now when we do this, it looks like all the base will be neutralized because we have more acid than we have base. And we will have left over, if we do this, if we subtract the two numbers, so actually rather subtract, and what we'll have is we will have 0.0005 moles of H+ left over. And again, if you want to make a note about it's all the base will be neutralized. So all this is neutralized, so if you subtract these two numbers, you will find out how much you have left over. Well, the pH that we want to try to find out at the end, remember we're going for the pH of the solution, it will be based on all the acid that's left over. But we need to find out the molarity of the acid. Molarity is moles over liters. In this case, we have 0.005 moles of our acid, and the liters will be total liters, which will be 0.045 plus 0.05. So we get 0.095 liters. So if you divide these two numbers by each other, you'll get yourself 0.00526 molar acid. So the pH is the negative log of that, of 0.00526. I'm going to take the negative log, and your pH is 2.28 using 3 sig figs. So notice what we've done as a recap. We added all the base versus all the acid, and because we're undergoing a reaction, we have to calculate how many moles of acid we put versus moles of base. And then we found out that it is this many moles of base, this many moles of acid. Looks like we have more acid, so all the base got neutralized or got cancelled out, and what we had left over was this many moles of acid. We solved for molarity and then negative logged it and found our pH. So we will do a number of these types of calculations for any portion of the titration curve, and this will conclude for us lesson 3 of chapter 17.